Prishawati, and today I'll be telling you about systems of equations. Let's get started. Today, we'll first talk about what a systems of equation is, what problems you'll see with this concept, the methods to solve systems of equations, which is graphing, substitution, and elimination, the different types of answers to substitution equation problems, one answer, no answer, and infinite answers, and finally, a word problem example to get you used to another way you might see systems of equations questions. So, what is a system of equations? Well, it's essentially a problem that involves two or more linear equations and two or more variables. You'll most likely see it as an equation problem where the question literally gives you the equations to solve. You can also see it as a word problem though, where you need to draft up two equations and then solve them. Usually these word problems involve money and involve either solving for a constraint based off of other factors or optimizing some sort of transaction. What I always like to remember is that the more types of problems you try and get used to, the better you will do on a later test. Knowing the approach is really 75% of the battle. The algebra is not hard if you have a solid understanding of single-step and multi-step equations. So let's talk about our first method to solve the system of equations, graphing. Although it's a great visual method, it usually takes too long to execute on every single problem. Therefore, I only recommend that you use graphing when the problem or answer choices require graphs. Even so, I remember that graphing is only needed to get a general idea of where the equations are, rather than an exact representation of the system. An exact representation usually takes too long and usually doesn't serve that much purpose due to the fact that most of the answer choices are multiple choice and will be clear-cut to see. To solve using this method, I also highly recommend that your equations are easily transformed into slope-intercept form. If you need more of a precise graph to differentiate between two answer choices, trying to graph an equation with a slope of -11/4 will usually not go well for you. Try another method instead, like elimination or substitution. A good example is this example. So it says solve 3x plus 2y equals 44 for x and y, and we also have another equation, 6x minus 6y equals 18. So the first thing I'm going to do is try to get this into slope-intercept form. So I'll keep my y on this side. Whoops. That's a little bit messy, but 2y equals -3x plus 44. And what we want to do is divide each side by 2 to isolate that y. So we'll get y equals -3/2 x plus 22. Okay, and our next equation, 6x minus 6y equals 18. What I'm going to do is I'm going to bring the 6y to this side and the 18 to the other side, just so that it makes it a little bit easier for me. So what I'm going to have is 6x minus 18. Oh, sorry, this is a little bit messy, but equals 6y. And what I want to do is divide each side by 6 so I can isolate my y, and I should end up with x minus 3 equals y. Okay, and let me just graph this. It won't be perfect, but I can try to give you an estimate. So we have plus 22, so we know our first graph is going to start right here, and we have -3/2, which means that I'll probably do a slope of something like this. And then x minus 3 equals y, so -3 is our y-intercept, so we'll be like somewhere down here. And x is obviously positive, and we're just going up, so I'm just going to do a little bit of this. So this is a little bit off-center. The real answer is supposed to be x equals 10 and y equals 7. As you can see, I didn't do a very good job of drawing straight lines. But The idea is if I saw this on an answer choice and this was the only answer choice of this like sort of shape, then I would pick this answer choice or something that looks like this. Okay, on to our second method to solve, substitution. It's usually used when you can easily manipulate one equation in the system to have one variable in terms of the other, and when your other equations are simple enough to plug the former equation into. For example, you could see y equals 2x plus 6 and 2x equals 3y plus 8 in your system, and you would know that substitution would be a good method to solve for the system. If it is hard to make one equation in terms of the other equation, or it's hard to plug in that former equation into your other equation, I don't recommend using substitution. I recommend using elimination because it would be a little bit faster. Remember that although we want to get the correct answer in our most comfortable way, we need to be able to switch our approach for the sake of time. In time tests, your time management is one of the most important things to have down. So I want you to be comfortable with all the methods I'm telling you about today, so that way you'll be comfortable enough to switch methods when time gets tight. Another tip with substitution, you want to make sure that the variable you're substituting for is the opposite of the one you want to find. Going back to my earlier example, y equals 2x plus 6 and 2x equals 3y plus 8 would be in perfect form if I wanted to solve for x, but I would have to rearrange that first equation if I wanted to solve for y, because I would want to have the y terms in terms of my x terms, so just isolate that x. Let's move on to an example, and we have the same problem. I'm going to substitute by manipulating my second equation because what I see is that I can easily divide both sides by this number and I won't get something weird. So let's just do that. I think I will just substitute for 6x because I am substituting for both x and y, and I'm going to have to do both of those separately. So it doesn't really matter which one I start with. And so 6x equals 18 plus 6y. And I would divide both sides by 6 in order to get x equals 3 plus y. Okay, and 3 plus y. And I would substitute this into the top equation. So I know x equals 3 plus y, so I have 3x here, so I'm going to multiply this by 3. So we'll have 9x plus 3y plus 2y equals 44. Oh, why did I say 9x there? Ignore that, it should just be 9. So we have 3y plus 2y, so that's going to be 5y. And if I add this 9 to the other side, I subtract this 9 from the other side, I'll get 35. So I'll have 5y equals 35. And then I'll just divide both sides by 5, and I should get y equals 7, which is what we saw in the graphing problem. And now that I know y equals 7, I can just plug it into one of these equations to solve for x. I think this bottom equation is a little bit more simple to work with, so I'm going to do that. 6y, so I would multiply 7 times 6, so I would get 6x minus 42 equals 18. And now 42 plus 18, because we'd add 42 to both sides, would be 60, and we'd have 6x equals 60, which is pretty easy to solve. We would get x equals 10. So as you can see, we got the same answer as we did in our graphing problem, and it is a little bit more work, but it's more easy to do this algebra and not have to draw out a very precise graph, because as you saw in the previous problem, I didn't even draw a very precise graph. So finally, the last method, elimination. It's one of my personal favorites due to how quick it is. It's usually used if one equation can be clearly manipulated to have one value be the same as the other equation. Essentially, we want to make sure that we wind up with either a y term with the same coefficient in both equations, an x term with the same coefficient in both equations, or just a constant in both equations. If you get some wacky coefficient to multiply an equation by to get the same term, don't sweat it. Just use substitution or graphing if you can to save you time. The process is essentially adding or subtracting both equations together. Since one variable is the same in both equations, we will cancel out that variable and we'll end up with a variable equaling a constant, which is easily solved. Like substitution, we want to make sure that we're canceling out the opposite variable to the one we want to find. This just makes it easier on ourselves to get the right value faster. Okay, again, we have the same problem. We're going to solve for x and y. So what I see is that we have 3x plus 2y equals 44 on the top there. And what I would want to do is multiply that by 2, so I can get 6x and 6x in both equations. So I can cancel that out. And again, I'm solving for x and y, so it doesn't really matter what I do. If I wanted to solve for specifically x rather than y by doing what I was doing, I would multiply this top equation by 3 in order to get 6y and 6y. It doesn't really matter the sign next to it because I could just change the operation I would use on both equations. So if we get two variables with the same coefficients and the same signs, I would subtract. And if I get two variables with the same coefficients but different signs, I would just add both. So let me go on to multiplying that top equation by 2. So I would get 6x plus 4y equals 88. Wow, that's pretty big. And we have 6x minus 6y. Oh, x. Sorry, that's a bit badly written. Minus 6y equals 18. Sorry, this is so messy, but yeah. Okay, so 6x minus 6x, these two cancel. 4y minus negative 6y, minusing a negative would mean that we just add, so we get 10y. And 88 minus 18, so 88 minus 8 is 80, 80 minus 10 is 70. And if we divide both sides by 10, we get y equals 7. And now we do the same thing that we did in substitution. We're just going to plug this into one of our equations. I'm going to plug it into that top equation because that seems a little bit easier. So 3x plus 20 equals, oh, sorry, why did I say y equals 10? Sorry, this is supposed to be 7. Okay, 3y plus 20, or 17, or 14 now, equals 44. And 44 minus 14 would be 30, so we'd have 3x equals 30, and if we divide both sides by 3, we'll get x equals 10. And boom, same answer as the substitution and the graphing. Okay, now here's where things might get a bit confusing. You can actually have different types of solutions. Apart from just the one answer problems, we can have cases of no solutions or infinite solutions too. No answers happens when everything has been cancelled out in both equations except for the constants. So you might get something weird like 5 equals 6. This signifies that the lines are parallel and therefore never touch each other forever, meaning that they're never going to have any solution. So let's say we have one line like this, one like this, and one line like this. This is an example. If you put both equations in slope-intercept form, you would get, and you graph them, you would get something like this. Think of it as both equations being like the same equation, but with different y-intercepts. infinite answers actually take the same process as no answers, but the constants that remain at the end do equal each other. This signifies that the lines are the same line, maybe one being manipulated to the bit to look like a different equation. So we'd have one equation looking like this, and the other equation would actually be the same line somehow. Sorry, they're not on top of each other, but it would be the same line. Okay, so for what value of a will there be no solution for this system of equations? So we have 2y minus 6x equals 28 and 4y minus ax equals 28. So what I see in here is that I see that this is multiplied by 2 in this equation, and our constants are already the same. So what I want to do is I kind of want to have one of my variables be the same as another equation to kind of get a feel for what I would do. So I'm going to divide this bottom equation by 2, because I think that's a little bit easier to divide 28 by 2 rather than multiply 28 by 2. So this bottom equation divided by 2 is 2y minus ax over 2 equals 14. And now I want to have this ax over 2 equal 6, because that would mean I would have 2y minus 6x equals 14, which means that if I set these equal to each other, I would have 28 equals 14, and that's not right, which means that it would be no answers. So that means that I would have a over 2 equals 6, and then I would multiply both sides by 2, and I would get a equals 12. And if I plug that in, you see that 2y minus 6x equals 28 and 4y minus 12x equals 28, which can't happen. We could also, this is a little bit slower, but it's very reliable rather than just looking and scanning. We could also convert these into slope-intercept form. So we would have 2y equals 6x plus 28 and we divide everything by 2, so we get y equals 3x plus 14. Oops, running out of room. So basically we want to have the same thing happen over here, but our constants would be different. And if I do the same thing on this side, I would have, I'm going to skip the step where I divide, so I'd have y equals a over 4 x plus 7, which means that a over 4 would have to equal 3, and if I multiply both sides by 4, I would get a equals 12 again. So 2 approaches. This one's a little bit more reliable. It's a little bit slower, but that's okay. And an example of an infinite answers problem. So for which value of a will there be infinite solutions for the system of equations? So what I see is that I could multiply this top equation by 1 and 1/2 and set it equal to solve. So I could try to get both equations to be the same. I say multiply by 1 and 1/2 because I know I can multiply 2y by 1 and 1/2, and I know I can multiply 28 by 1 and 1/2 because this is even and this is even. So if I multiply this by 1 and 1/2, I should get 3y and remember multiplying by 1 and 1/2 just means multiplying by 1 and then adding 1/2. So minus 9x. It's a bit weird, equals 28 divided by 2 is 14, 14 plus 28 is 42. So we have 3y minus 9x equals 42 and 3y minus ax equals 42. We want to have the ax equal 9x, because if both the equations are essentially the same, that means that we would have infinite solutions. So if 9x equals ax, then a equals 9. And we're done. We could also do the same thing where we convert both to slope-intercept form. And I won't do it now just for the sake of time, but you can reference the previous slide on how to convert these both into slope-intercept. Okay, and now we have a good example of a word problem using the same skills that we've applied so far. The only difference is that we have to make our equations. They will actually be a little bit easier equations to solve than other problems where they just give the equations to you. So that's always nice because they give you the extra step of making the equations. So a movie ticket is $4 for children and $9 for adults. Last Saturday, there were 680 moviegoers and the theater collected a total of $5,235. And how many moviegoers were children on Saturday? So I would set up my systems of equations like this. So in terms of money, I know that it's $4 per children, which I'm going to call x. X is the number of children, plus $9 for adults, I'm going to call adults y, equals $5,235. Just fix that. And then in order to know how many total moviegoers there were, we need to add the number of adults and children. So we would get x plus y equals 680. Now, you can do substitution and you can do elimination on this. I personally like to do elimination because I think it's a little bit faster. Since I want to figure out children, I want to keep children not touched, so I'm going to try to eliminate adults, which is this y variable. What I would do to use elimination on this problem is I would multiply everything by 9, so I get 9y and 9y, and 680 times 9, I'm just going to do that on my calculator, but you can always do a regular multiplication. That would give me 6,120. And since this number is bigger than this number and this number is bigger than this number, I'm just going to subtract that way. So I would get 5x equals 6,120 minus 5,235. And again, I'm just going to do that on my calculator. If you don't have a calculator, you can always just subtract. And I will get 885. And now all I have to do is divide both sides by 5, again, using my calculator. And children should be 177. I just find elimination a little bit easier in this case, but you can totally do substitution because you have an x plus y equals 680, and that's a really easy equation to just isolate one variable. And now we have a bonus tricky problem. So I'm going to have you pause this video here if you can try to figure it out, and I'll go over how to solve it in 3, 2, 1. Okay, you solved it? Great. Let's get started on explaining how this problem works. So the trick to solving this problem is recognizing what an average is. It's the sum of all terms over the number of terms. Therefore, the average of A and B will be A plus B over 2. That's A plus B is the sum of all of our terms, and we only have 2 terms, so we're going to just divide by 2. So what I see in this equation is that if I add both equations up, I will get 8A plus 8B equals 40. And that means that I can get a clear equation where I can just solve for A plus B, which makes my life a whole lot easier. So if I add these equations, equals 40, because I would just add the constants. I can divide both sides by 8, sorry. A plus b equals, and 40 divided by 8 is 5. So since we know a plus b equals 5, we can just have 5 over 2 as our average, and that would just be 2.5. And boom, very quick problem. Again, sometimes you may not always figure out the trick, in which case I would suggest that don't panic. Just try to find the value of one variable using some of the methods that you saw before. If you can't find a trick, always go with what's tried and true. And that's all, folks. Thank you for listening and have a wonderful day.